This is the third, the week three TA session for structural analysis course taken by Professor Amit Shah. I am Trisha Chakraborty. I'm one of the course teaching assistants. I'm a first year PhD student at the Indian Institute of Science, Bangalore. Uh, I start with a recap of the previous 2 weeks. In the first week, we looked at why the motivation behind studying structural analysis. We saw what are the types of internal forces that we encounter: axial force, bending moment, shear force, and torsional moment, and how they manifest in a structure. And then the common classifications of types of elements like truss element, beam element, frame element, and common boundary conditions like hinge support, roller support, or fixed boundary condition or internal hinge. Then we looked at structural indeterminacy, that is has to do with stability of a structure, the difference between the number of equations and the number of unknowns. If the number of unknowns is more than the number of equations, the structure is indeterminate, that is overly safe. And if the number of unknowns is less than the number of equations, then it is an unstable system. And if they are equal, then it is a determinate system, which is easy to solve. But in practical, most structures are indeterminate. And lastly, we looked at the bending moment and shear force diagrams. How if of beams, how if a beam is given and the loading conditions and the boundary conditions are given, then the pattern of bending moment and shear force, how they vary along the length of the beam. So the BMD and SFT, which is a very important topic of structural analysis. Then in week two, we looked at mostly at trusses, idealization of trusses, how the kind of trusses we see in the real world and how they are idealized using line elements, and stability of trusses, which again has to do with indeterminacy, external and internal indeterminacy, and the solving the member forces in a truss. That is, the truss configuration is given, the boundary conditions, the loading is given, and how to solve the member forces. We looked at two methods: method of joints and method of sections. Method of joints is used when we need to find the forces in all the members of a truss, and method of section is commonly used when we need only in a few members. So if we take the sections, if we learn to take the sections carefully, we may end up solving a lot lesser equations to solve the exact forces that we want. And so now we are in week three. The major topics are the principle of virtual work and the unit load method to determine displacements in a truss. The work done by a force, as we have studied in plus 2 as well, is that if a force acts on a body that moves along this path AB. So this, and ds is the direction of motion at each point. Ds is it is a differential displacement. Then the work done will be fs ds, from the first initial point to the final point. So if we go from A to B, then the force, if this f dot ds, I mean f, it will basically be f ds cos theta. From A to B, it will be integrated because at every point the theta is changing. And there are two kinds of forces related to the work done. The one is conservative force, where the work done is path independent, for example gravity. The non-conservative force, where the work done is path dependent, for example, the work done by a force is defined as the integral of force dot displacement, the differential displacement when we go from point A to B. It will be the dot product of the force into the differential displacement, that is fs cos theta, f ds cos theta, from A to B. There are two kinds of forces related to the work done by it. One is a conservative force, when the work done is path independent, for example gravity, and another is non-conservative force, where the work done depends on the path, for example friction. Like here we see that this is the work done by gravity. If we drop a mass from a height of h, then as we have learned in plus 2, the work done will be mg into this distance, this h. So uh, even so, now if this mass is dropped straight, the work done by gravity will be mgh. And then suppose we have a channel or something where the mass moves like this and comes, but so long as the final height and the initial height and the final height are same, the work done by gravity will remain the same, it will remain mgh. So gravity is a conservative force. But friction, on the other hand, is a non-conservative force. Friction is when this is a normal reaction of if a body has a mass m, and then if it rests on a surface, then the reaction will be mg, and that will be the normal reaction. And friction is static friction acts as mu into n, where mu is the coefficient of friction. Now if we move it for a distance x, then the work done by the friction force will be mu n into x. Now, but if this I take it from this point to this point, it will be mu and x. But if we take, even if the final point and the initial points are the same, and we take it over a longer path, like if we make a circuitous path, then the work done will be mu n into that length of the path. So the length of the path comes into the question. So friction is a non-conservative force, while here only the difference in height between the first point and the last point mattered. At equilibrium, a structure, this is a principle that a structure deforms in such a way that its potential energy is minimized. This has two implications: that external loads should be equal to the internal forces, and external work should be equal to internal work. Now the manifestation of this is a little maybe a little hard to imagine. So this is the principle, though we will explain this through the concept of virtual work. Virtual work, why is it called virtual? Because it is not either the force, work is force into displacement, basically force dot displacement. Then the work term virtual comes because either the force or the displacement has to be virtual. It is, see, work done by a real force acting through a virtual displacement, or a virtual force acting through a real displacement. For example, this spring mass system is in equilibrium. This delta, this is a real displacement. This force is real. This mg force that is acting on the spring in the downward direction is real, and this delta is real. So this is equilibrium condition. Now from the equilibrium condition, let us consider a virtual displacement. It is not actually happening, but if suppose we imagine there is a delta star and additional displacement in the downward direction, then this delta star is the virtual displacement. And what will be the work done by the virtual displacement? This work is done by the real force. The real force here is mg, this because it's the mass of the system, and the g is acceleration due to gravity acting downwards. So the virtual work done by this real force is mg into delta star. Now the question comes that why are we talking about virtual displacement? This was in equilibrium. What was wrong with it? But now this is the principle of virtual work, that in equilibrium the virtual work of the forces applied to a system is zero. So the this basically this mass is under two forces. One was mg down this point, one was mg downwards, and the other is the internal force, which is the force developed in the spring. So this is how it works. Mg into delta star is acting in the downward direction. This F into delta star is acting in the upward direction. And since the work in this, if we want this body to be in equilibrium, we have to equate the virtual work of the forces applied to the system, like from in the opposite direction. So you could also write it as mg delta star minus F delta star equal to 0. So we get F equal to mg, which is obvious from here as well. Like if you forget the virtual displacement and solve this the way we solve equilibrium, if we equate the forces in the y direction, we will get F equal to mg. And this is another way of looking at it. It may look unnecessary, like why are we going into the virtual displacement when we could have just solved the equilibrium? But the principle of virtual work is a very important principle in structural analysis. So it has many implications later on, like it makes a lot of calculations easier, where equilibrium would not be that easy to solve. This is the application of principle of virtual work that we are going to look at now, the unit load method to find deflection of trusses. Now we know that a response of a structure basically can be of two types. First is the forces or the stresses generated in the structure. This is related to the collapse limit state. Now that, for example, in a building the beams and columns are the framework of the building. So in a building, the a building stands on the beam and column framework, and the this collapse limit state is related to that, as the name suggests, that the building should not collapse. That means the beams or the columns should not collapse. What does that mean? Every material has an yield strength beyond which, if you stress it, it will break, it will yield or break. So This is related to that the force generated in the beam or the column, or the stress, that is the force per unit area, should not exceed the capacity of the structure, the yield stress or the breaking stress of the structure. So that is one important response of a structure, that what are the forces or the stresses developed in the members. And the second one is displacement or strains, which is related to the serviceability limit state. For example, it may seem more unimportant than the collapse limit set, because of course our first job as civil engineers is to ensure that the structure does not collapse. But serviceability is another thing that, yeah, serviceability is another important criteria. For example, in a factory shed, suppose a beam, it is not failing, but it is bending a lot, and the midpoint is deflecting a lot. It may hamper the working of certain machines. Or for example, or in a residential building, suppose a column has swayed sideways and deflected, then it will look unsafe. Maybe suppose it is not collapsing. Suppose the forces or stresses are not exceeding the limits, but it will tilt, and the common people will raise an issue to it. They will say that it is unsafe, the structure will look unsafe. And then that is why in our codes, in the Indian standards codes or in any code in the world, there is also a criteria placed on serviceability, that is the members cannot deflect beyond a certain limit. If it deflects beyond those limits, even if it does not collapse, even if the structure is intact, if the displacement criteria is exceeded, you have to redesign the structure to be more to have a larger section or something. So the response of a structure can be classified into two: the forces and the displacements. Now in the last class, when we studied the trusses, you remember what we did? We took the truss, we took its loading and its boundary conditions, and we found out the member forces in each of the elements, in each of the members. So that was related to the forces generated. From that we can get the stress easily, because the trusses generally if you assume they have a uniform cross sectional area, you can divide the force by the area and get the stress. But today we are going to look at the displacements at the nodes. So in a truss, the two important criteria things that we need to, as structural analyzers, the things that we need to find out are the member forces and the nodal displacements. In week 2 we studied the member forces, and today we are going to take a look at the nodal displacements. For that, we use the unit load method, which is based on the principle of virtual work. The unit load method is a technique to quantify displacements and rotations of the equilibrium configuration of a structure. That is the shape of the structure after it has managed to equilibrate the applied force loads. Now, as I have said before, that unless there is equilibrium in a structure, we won't be talking of it. If a structure is unstable, then it is not a structure at all, it is not permissible, so we do not care about it. Only once a structure is in equilibrium, it is stable, then we will calculate the forces generated, uh, or the displacement and rotations. And now another important thing is, when we say displacement, we use the term displacement loosely, but it includes both displacement and rotation. Displacement is related to translation and the slope, and rotation is related to the slope of the of suppose a member at some point. So the displacement response includes both of these. So the unit load method is used to, suppose when we have a structure in equilibrium, we want to find the displacements or rotation of various points of the structure, then we use the unit load method. The virtual unit For this method, the basic idea is, we will apply a virtual unit force at the node where we want to calculate the displacement. And these So suppose we want to here displacement is being used only in the translational sense. So if at a node I want to suppose calculate the horizontal displacement, so I will apply a horizontal 1 kilonewton or kilonewton, the unit you can choose based on whatever the units of the applied loads are given. You will apply a force of 1 kilonewton at that point in the horizontal direction. Similarly, if you want to find out the displacement in the vertical direction. So, similarly, if you have a node and you want to calculate its displacement in the vertical direction along the y-axis, then you will apply a unit force of 1 newton or 1 kilonewton along that direction. And the analogy is, suppose you want to calculate the slope, then you have to apply a virtual unit moment like 1 kilonewton meter. Suppose the units again you can choose, and we have to and And since we are talking about 2D objects, we have two translational degrees of freedom and one rotational degree of freedom. The translation degree as are like in along the x-axis, along the y-axis, and the rotational degree is out of the plane, like clockwise or anti-clockwise. So we will apply a moment into the plane or out of the plane along the z-axis, basically that is coming out of out of the surface that the truss is sitting on. So, and then see, since we talked in equilibrium, the external virtual work and internal virtual work have to be equal for a structure to be in equilibrium. Now, if you apply a unit force, then the external virtual work will be 1 into delta. Why is that? Because 1 is the force we are applying and delta is the displacement of that node that we want to find out. We do not know the value of delta yet. And there is no cos theta term here. This is, I mean, a dot product, but there is no cos theta because, as I said, if you want to calculate the horizontal displacement, you will apply a horizontal load. So the angle between the two becomes 0 degree, and cos 0 is 1, right? So for a unit force, the external virtual work will be 1 into delta. And similarly for a moment, if you apply a moment, then the and you want the slope. For example, if the slope you want is theta, then the external virtual work will be 1 into theta. 1 is the moment, magnitude of the moment, and theta is the slope. And since external virtual work equal to internal virtual work for a body in equilibrium, equilibrium is taken for granted. Then 1 into delta is equal to internal virtual work. That is, here delta is internal virtual work. So if we can find out a method to find the internal virtual work due to that unit load, then we can find the displacement that we are wanting to find. So these are the steps for, see, this unit load method has applications in a very wide sense, like for example, solving indeterminate structures. So far, remember, we have only solved determinate structures, like for example, in a 2D plane we can have three equations of equilibrium. So far the number of support reactions we have been considering three. We have not been considering more than three. How we will solve the structure, they will come in the later weeks. But so the unit load method has a lot of applications for a lot of structures. It is one of the, I mean, the principle of virtual work is one of the most important principles we use in structural analysis. But for now, for this week's work, we are just interested in finding the nodal displacement of a truss. These are the nodes. These circled marked things are the nodes. So suppose, and it has the truss has a configuration, a certain loading pattern, certain boundary conditions, and suppose we just want to find out the displacement at one of the nodes, whatever the node be. So what is the first step? Due to given load system, we will calculate the forces in all the members. For example, we are just calling it the P system of forces. Like if there are n members, we will call the forces P1, P2 to Pn. And this force system can be calculated using the method of joints. We talked about the method of joints last week, and we also talked about the method of sections. But why are we why are we saying method of joints? Because then the thing is, method of joints, since it goes systematically from one joint to other, it goes to all the joints. It is used when we want to find out all the member forces. But the method of section will be used, suppose if we needed to find the force in only 2 3 members, then we will cut a section like this or something and try to find. But for this method, you have to find out the member forces in of all the members. So the number of members is n. You will end up with p1, p2, p3 dot 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 to pn. You will use a method of joints. Then the step 2 is, forget about all the external loads. This W1, W2, W3, whatever was being applied, you remove them. You keep the truss, you keep the same boundary conditions, and you apply a unit load at the node. As I said, suppose here you want to find out the nodal displacement of this node C in the vertical direction. So what will be the loading condition of the truss? Now you will remove all the external forces and you will just apply a unit force here. You will apply a unit load 1 kilonewton at this C in the downward direction or the upward direction. I'll tell you the implication of that choice later. So remove all given external loading and apply unit loading at C in the direction of the desired deflection. Due to unit load alone, find the forces in the member. Again you have the same truss, but you have a different loading condition. So again you have to find out the force generated in each member due to that unit load. So again you will get a set of n forces, right, in each of the members. So k1, k2, k3 to kn. This will be called, we call the K system of forces. And this, the formula that we will use is in step 3 is a deflection of joint C in the direction of applied unit load is given by delta C is sigma PKL by AE. What is L? L is the length of the member we are talking about. So we this sigma is member wise. Like for each member, you know the P, you know the K, and you know the length. So you multiply those, and for each member you find out this PKL product. Then you add all of them, and then you divide by the AE of like the cross sectional area and the Young's modulus that by of the entire structure. Now of course, if in common questions like what you are expected to encounter, you will mostly get the same cross sectional area and Young's modulus for all the members. But if they vary, then you put the summation outside. Then for each member individually you have to calculate PKL by AE and add that. And see, if this value comes out to be positive, the deflection of the joint C will be in the direction of the unit load. For example, you have applied a unit load in the downward direction and you end up with a positive delta C, suppose. That means C is deflecting in the downward direction and the magnitude is this. But if you apply the unit load in the downward direction and the magnitude of the delta C comes out to be negative, that means C has deflected in the upward direction, and anything can happen, right? I mean, you can see a structure and maybe you can, by intuition, you can say that this in this structure C will deflect downwards, but don't take it at face value. Calculate properly with sign and then interpret the sign. And the calculation of the deflection or truss is generally done in a tabular manner. This is the format of the table to be followed. You will list down the member names. You will number all the members first to help you keep track of it. You will then you will solve the truss first with the existing loading conditions. Then when you are solving the P forces, you won't apply the unit load. When you are solving this, you are just taking the external load that has been given to you. So you will write down the force developed in each member. Then you will remove the external forces. You will only apply the unit load of the node you want in that, at the node you want in that direction. And you will write down the k's, the k forces. Then you will write down the length of each member that will be given, or you may have to calculate that from geometry. And then you will find out the product, because I mean this table actually helps you to calculate. It is not mandatory, but if you do it in a systematic manner, the chances of getting mistakes reduces. So you will get a PKL product for each and you will add them. And remember, pay attention to if the cross sectional area and Young's modulus. See, Young's modulus has a very less chance of varying because you are mostly constructing it of steel or of same member, and Young's modulus is a material property. So Young's modulus will remain the same for all the members. They're almost 99% sure, but the cross sectional area may vary. Like suppose in a truss, you expect because since you know the kind of loading. For example, in a bridge, you know the kind of loading that is going to come before you even analyze it. So you can anticipate that in certain members the force developed will be greater, and you know that stress is forced by areas, right? And it is the yield stress or the breaking stress of steel that has a limit. It is, I mean, a steel member does not know what force is. I mean, it doesn't break based on what the force is being developed. It breaks based on the stress. So if you anticipate that in certain members the force is going to be higher, then we often give a thicker section, I mean a wider section with a greater cross sectional area, so that the stress will be less. So that if the area of all these members are given different, in this table also add a column with A and find out PKL by A. That you have to remember. Don't just blindly follow this. Then we have to add that and then divide the overall thing by the Young's modulus. And this is, I mean, if you see examples, it will become clear. For example, let's start with a simple two-member truss. This is an equilateral triangle. These are the two members of the truss, and this is L. So both of these are L as well. So we'll consider this joint C. At this, we first find out. See, firstly, mostly in trusses or whatever, bending moment diagram, shear force diagram, whatever we have done, I generally say the first step is calculating the support, calculating the reactions at the supports. But if you can avoid it, definitely go for it, because in the competitive exams there will be time constraint as well. So by with practice you will start identifying whether you actually need that or not. Here what do we need? We have two members, so we need the forces at the two members. So if we consider this joint, the equilibrium at this joint, we can directly find out the member forces CA and CB. So we are considering the joint C. At this point we have two equations of equilibrium in the method of joints. At each joint we have two equations. That summation of the forces in the x direction will be 0, summation of forces in the y direction will be 0. So consider this, the sigma fx is 0. So this in this P is being applied in the vertical direction, so it does not have any component in the horizontal x direction. But this CA, PCA cos 30 degree, we are taking it minus because, as I said, in method of joints, by default we assume the forces away from the joint, and if we take this direction, the right side to be positive x-axis, we will get minus a PCA cos 30 degree because it is oriented at an angle of 30 degree with the x-axis, minus PCB again cos 30 degree because it is also oriented at 30 degree with the x-axis is 0. So we get one equation that PCA plus PCB equal to 0, and adding up the forces in the y direction, we get, see, PCA sine 30 degree is oriented upwards, minus P, which is the applied load, minus PCB sine 30 degree, because this one is downward. See, this we have taken this force in this direction, so its x-axis force is in the downward direction, is in the left direction, and the y-axis force is in the downward direction, so it is minus. However, for CA, you can see that if the force was like this, the components, when you split it into components, along the x-axis it will be along the negative x-axis, but for the y part it will be in the positive direction. So this is the second equation, and solving it, you get that PCA is plus P and PCB is minus P. What does these imply? Plus and minus. Plus implies tension, minus implies compression. The way we have taken, if we take the forces initially, assume the forces to be away from the joints, then positive implies tension and negative implies compression. But for now, since we are interested in finding the deflections, you need not interpret that. Just keep the signs. You have to keep the signs. When you put it in the table, you have to include it with sign. Then, the case system of forces. We have we need to find out the, in this question we need to find out the vertical displacement of this joint C. Okay, so we will forget this P, we will remove this P, and what will we do, we will apply a load of one, whatever unit of this P is, we will apply a unit load 1 here. So you can see that since if you remove the unit load, the load P, and apply unit load at that C, this will be C in the downward direction. The KCA and KCB will be plus 1, plus and minus 1. How do we get that? This is a step jump. Basically, this equation will remain the same. I mean, put K in place of P. This equation will remain the same, and here it is 1, right? So PCA sine 30 degree minus 1 minus PCB sine 30 degree will be 0. So PCA will be KCA will be 1 and KCB will be minus 1, and you don't have to solve it. The interesting thing is that if there is only one force in a structure and that you are replacing by a unit load, there is a principle of linear superposition. Like in linear elastic bodies, there is a principle of superposition that implies that if the force is multiplied by a factor alpha, then the member forces will also get multiplied by that same factor alpha. So here, this when you are calculating the K system of forces, you remove this P and you put a 1, right? So you are dividing the load applied by 1 by P, so the member forces will also be divided by P. So KCA will be 1 and KCB will be minus 1. Keep, and the sign will remain the same. So the deflection at C will be, the as per the formula, sigma KPL. So 1 in plus 1 into plus P into L, plus this plus is because as this plus will, I mean, this term will come as many times the summation as many members there are two members in this, so there are two terms that we have to add, 1 into P into L plus minus 1 into minus P into L by AE, because here the cross sectional area and Young's modulus was same for the both the members. So we get 2PL by AE. And if you see the units, you will see that basically this has the unit of length, because a quick way to check, you can see, is P by A has a unit of stress, and you know that Young's modulus also is Newton per meter square, right? Young's modulus has a unit of stress. So P by A is Newton per meter square, E is Newton per meter square, that gets cancelled, and the L's unit remains. So obviously, you have to keep in mind that you have to put the units consistently. Usually in structural analysis problems, the forces are given in kilonewton, not Newton. So if you put the P in kilonewton and the A in millimeters, then you have to convert the Young's modulus also in that units. Like, you have to convert it into Young's modulus also into kilonewton per millimeter square or Newton per meters, or convert this P by A into Newton per meter square. Remain consistent with the units, and the L, whatever unit you put it, if you put it in millimeter, the deflection will come in millimeters. If you put in meters, then the deflection will come in meters. So that this is one very important thing, because normally in the questions they will give mismatched units, they will give the common units that are being used in for different quantities, but you have to be careful about that and put consistent units. So we get the deflection of C, and the note that we found positive, positive. So what does that imply? Since we had the unit load also we had applied in this direction at C in the downward direction, that means this node C is deflecting in the downward direction. And just for example, suppose, because initially when you are solving the problem you don't know which direction C is deflecting, right? So you could have just assumed, you could have just put a unit load in the upward direction as well. Forget P. If you put a unit load in the upward direction, then you will see that the K will come out in the with opposite signs, and ultimately you will end up with minus 2pl by AE. That will again imply the same thing, that unit load we have applied in the upward direction, but the delta C comes negative. That means the deflection is in the opposite direction, that is in the downward direction. Whichever sign, whichever way direction you apply the unit load, you will get the sign accordingly, because the structure's response remains constant irrespective of whatever unit load you apply. Okay, so this was a simple example. We move to the second example. This is a three-member truss. So here they are solving the reactions first. This is RP, this is RR, and this this is HR. This is a hinge and this is a roller support. So these concepts remain same. These concepts should be clear to you by now, because you have solved these support reactions in beams, then in trusses. So, and we have applied a 135 kilonewton load at the this point. So we have three equations of equilibrium. One is redundant here because there's no horizon. Sorry, there is no vertical loading, so that equation we maybe don't need. We have three equations of equilibrium, that is delta fx is 0, delta fy is 0, and delta mr is 0. Mr is not necessarily has to be r. You can take moment about any point and conserve it, it will be 0. So for the first equation we take is delta fx is 0. So what are the forces in x direction? HR and 135. So HR is 135 kilonewton. And we take a moment about R. Why do we take about R? Because there are two forces passing through it, and when you take moment, force into distance will become 0 for two forces. So the RP will come out directly. So RP will find RP into 4.5 gives a clockwise moment that you have taken positive, and 135 also gives a clockwise moment about this point R, and its lever arm distance is 6 meter. So you get RP is minus 180 kilonewton, and this is where you apply that sigma Fy is 0. If a force of minus 180 kilonewton acts here, then a force of 180 kilonewton has to act here, because there is no applied vertical loading. So we have found out the support reactions. Now what is our next step? We have to find out, for this external loading 135 kilonewton, we have to find out the member forces in all three members. So let us look at this joint R. At this joint R, these are the support reactions: 180 kilonewton upwards, 135 kilonewton towards the left, and we have two members here, RP and RQ. We have taken these arrows away from the body, so we get this is a very easy to solve, because this is oriented in, if a member is oriented along x-axis or y-axis, you can directly apply these. So you can see that since 135 is in this direction, PRP must be minus 135 kilonewton, so it must be under tension. And for this, since 180 is directed upwards, PRQ must also be minus 180 kilonewton, it is also under compression. And now that we have these two forces, we move on to this joint P to find the force PQ. This is PQ, and here we need one. In any one equation we can take. So PQ sine theta, that is the vertical component, plus 180 degree. This is the support reaction at P. We had found it out to be 180, no, so it is directed downwards. So PPQ comes out to be 225 kilonewton positive. So this is under tension. Anyway, tension and compression actually don't matter here. Just keep the signs. Now next what we will do, we will forget about this 135 kilonewton, and we will apply a unit load. And again, since this and we want the deflection at point Q, suppose, and again, since there is only one load in this structure, and this load, when you remove the 135 kilonewton and put a 1 kilonewton force in this place, by the principle of linear superposition, the developed forces in each member will just be divided by 135. This is not applicable if there were two forces. If there were two forces applied on a structure, two or more forces, and you divide one of the forces by a certain factor, the member forces will not just vary in that in will not be divided by that factor. So but if you have, suppose you have five forces on a structure and all five are divided by the same factor, like all are divided by a factor of 2, suppose, then the member forces will be divided by 2. Basically you have to replicate the structure exactly, like the loading pattern exactly, and in the for the pattern of the loading you need the ratio between the forces. You need to conserve this. For example, this is 135, and suppose there was a 135 in this direction as well. So if both of them we converted into 1, then the member forces will be divided by 135. But if this you let remain 135 and change the other force to 1 kilonewton, you have to solve the system again, because the loading pattern is no longer the same. But here there is only one force, so it is easy. And you k is p by 135 for each members. So here you write down in the table, see, you note down the three members, pq, qr and rp. 225 minus 180 minus 135 as we solved here. Then you divide these by 135 and get this. And the L's you have to calculate from geometry. I mean 4.5 and 6 are given, and by the Pythagoras theorem you can get this as 4.5 square plus 6 square, root of that as 7.5. So PKL you multiply and you get this, and you add these three. You add these three and you get this. I hope you're following it. Like you multiply PKL for each member and note down, and then you add all of these and you get this. And finally you have to divide by A into E. These values will be given. These values will be given in the question. So you will get end up with a displacement, and displacements mostly will be in millimeters. Of course, you won't expect a truss to deflect in meters. So if you are getting in meters, then something has gone wrong. Just keep that in mind. I mean, you won't be given unrealistic structures. One thing about civil engineering is that in questions you will be given, since the values will always be given realistically, you have to expect a realistic result. If you see you get 15.68 meters, you have almost surely made some mistake in units here. So check your units again. And again, look at this. Here we wanted the deflection of q in this direction. Now suppose we wanted a deflection of q in the vertical, in the horizontal, in the vertical direction, in the y direction. Then what would you have to do? You will first solve the p system, that is the same, that remains the same irrespective of whichever node you want to find the displacement at. But if you want to find out the vertical displacement at q, then when you remove 135 you will put a 1 kilonewton force at this node q in the upward or downward direction. Then you have to solve the structure again. Okay, again you can't just divide it by 135 if the direction is different. Of course, is this, I mean, the previous question and this one became same in the sense the force was applied in which direction, in that direction only we wanted to find out the displacement, so we could directly divide. But otherwise, if you wanted in the vertical direction at q or in the horizontal direction at p, because this is a roller, so it is constant in the vertical direction but it is free to move in the horizontal direction. So suppose you wanted the horizontal displacement at p, then you would apply a unit load at p here, like 1 kilonewton, remove the 135, and then you have to solve the structure all over again. This is just a shortcut that you can apply in the competitive exams. And so okay, so we get delta q as a positive quantity. That means that since we had applied the unit load in this direction, q is being deflected along this direction. Now, this is another example. It looks very complicated, but if you remember the concept of zero force members is like if three members meet at a node, two of them are collinear, and there is no applied external load or boundary condition at that node, then the third, the non-collinear member, will be a zero force member. So this is a zero force member. So this doesn't exist. If a force undergoes zero force, you can as well as omit it from your diagram. So if this does not exist, then if you take this node, these two members are collinear and this is non-collinear. So again, this is a zero force member. And coming from this side, this is a zero force member because these two are collinear and this is not. And from that, this is also a zero force member. And considering this joint, since this and this are both not non-existent, this is a zero force member. And again, uh, if you consider this node, since all of these are gone, this will also be a zero force member, and symmetrically all of these. So the structure will basically come down to this. This is, see, just see the difference. If you don't study the structure properly and identify the zero force members initially, you would have to solve so many members. But here you can just solve three members and be done with it. So always, if when you get a structure first, just keep an eye out for them. So all the interior members will carry zero forces, and when you are solving this structure for the forces, for the p forces, this you will find that at this joint, if you consider, you will see that is p by root 2, p by root 2. You don't have to solve the support reaction initially. This you will get, and in this you will get a force of p by 2. These are compression. P by, you can understand, even you can visualize, like in this truss, if you put a force from top, these two member will get compressed. This you can probably cannot visualize, but this will be under tension. So the forces in these two members are minus p by root 2, and this will be plus p by 2. And now suppose you want the deflection at C, then you will forget about the P, and you will put a unit load in this direction. So the forces will again get divided by P, 1 by root 2, minus 1 by root 2, minus 1 by root 2, and this will be plus half. This is our P system of forces, this is our K system of forces. And if this is 2L and this is L, then you can find the length of these members using trigonometry. And assuming tensile forces are positive and compressive forces are negative, the deflection at C you get as delta C is something like this, which you get positive. That means that the deflection was in the direction we applied the load in. So C deflects downwards. And we come to another example. This is in this question is is different from the previous ones, because here we are considering the displacement at I mean, we want to find out the displacement at a point that is where we are not applying the force, like we are applying the force here, but we want to find the horizontal displacement of the roller support of the truss, right? And in this point, sorry, this is the roller support, so we want to find out the deflection of node B in the horizontal direction. Node B does not have any deflection in the vertical direction, of course, because roller support constrains vertical movement. So we are given the truss configuration. There are no zero force members. Okay, this is a zero force member because these two are collinear and this, so you can omit this. And first we solve the reactions. This is HA and RA are the two reactions at the hinge, and RB is a reaction at the roller. So Fx is from sigma Fx equal to 0, you get HA equal to 100 kilonewton. Sigma Fy equal to 0, you get that RA plus RB will be 300. Be consistent with sign again. RA and RB we have assumed in the upward direction, and 300 in the downward direction. And we take the moment about one of any one point. We can I would have taken about this point because two forces will have no contribution. Okay, it's the same, it comes down to the same whether you take moment about A or B, because this HA has no distance. I mean, you can understand that HA provides no moment about B, because the line of action of HA actually passes through this point B. So if you take the moment about B, you will get contributions from RA and from these two applied loads. So RA into 9, because all these bays are 3 meter, 3 meter, 3 meter, 3 meter. So RA into 9 in the clockwise direction, which we assume to be positive, plus 100 into 4, this is 4 meters, so 100 into 4 also in the clockwise direction, minus 300 into 3 because this is in the anti-clockwise direction. So from that we solve RA as 55.55 kilonewton, and from this we already had RA plus RB is 300, so we get the value of RB as 244.45 kilonewton. Now we have to solve the P system of forces. We have the existing loading conditions. We have two loads now, and the way we have learned method of joints. We have to go systematically from one joint to the other. We start with joint A. At joint A, what are the forces? We have 100 kilonewton. We have 55.55 kilonewton here, and two members meet here, AF and AD. So PAS, PAD. The at each joint we have two equations. So the delta Fy equal to 0 gives PAF sine theta, because this angle is theta. This angle we have called theta. Okay, this angle we can find out. This theta, of course, we can find out because we know this length, we know this length, so we can find out the cos theta sine theta from trigonometry. So PAF sine theta is in the upward direction, plus 55.55 is 0. From that we get PAF as a minus something, that implies compression. And from equating the forces in the horizontal direction, we get PAD plus PAF cos theta equal to 100. PAD has a no, of course it's, I mean, it's oriented along the x-axis, so the theta doesn't matter here. But PAF has a component in both directions, and from that we get, from these two equations, we already know PAF. Putting that here, we can get PAD as a tensile force of this magnitude. Now what we have, this force and this force. Then we move on to this joint D. The joint D, at joint D there are three members meeting. We know the force in AD now, and DF is zero because we can say it's a zero force member because AD and DC are collinear, and there is no applied force at this point, and only DC is unknown right here. So in here you can see that at AD and DC are collinear, so the force in AD has to be equal to the force in DC, because DA and DC, whatever, because you have to conserve the forces in the x direction, and there is no member in the y direction. This is a zero force member. So since if AD was 141.66 kilonewton in tension, this will also be tension. If, I mean, if this is plus, this will also be plus. And then we move on to joint F. This is joint F. This has four members meeting. Of course, in for the method of joints, since we get two equations for at each joint, we cannot solve more than two member forces at a time. But since we know that we have already found out F, this force in this member, and this member is a zero force member, so basically we know the force here, or this member doesn't exist at all. So we have two unknowns, PFE and PFC. So this is how we draw it. This is they have dotted this out because this does not exist. It's a zero force member, and here we also have an applied load. Don't forget that these four members are meeting at this joint, and there is also an applied load here. So there are four active forces that we have to consider. PFC is PFC sine theta. This is PFC. Its sine component is oriented downwards, so that is equal to this 66.44. Would that its sign component is directed upwards, so they are equal. And PFC we get as something, this 69.44 in tension. And when we equate the forces in the x direction, what are the forces? First, the 100 kilonewton, the applied force, plus this force 69.44. We have replaced this. See, we have replaced this force, this, I mean, this member, this AF, by its force. This AF was under 69.44 compression, right? That is why this arrow is pointing towards the joint. Since during in the method of joints, we initially assume that the forces are pointing away from the joint because we assume tension is positive. But then we found out that this member AF was under compression, so when you apply it here, you have to put the arrow pointing towards the joint at 69.44. So this you have solved this, and from when you are equating the force in the x direction, you get 100 plus this PFE, which is the force in this member, plus 69.44 cos theta. Now the cos theta component is along this x direction, and PFC also has a cos theta component in the x direction. So all of them are positive because all of them are currently their components currently lie in the point towards right, towards the positive x-axis. So from that, we already know PFC, so we can find out PFE as minus 183.33 kilonewton. That means it is under compression. Now, what are the members we have solved? We have solved this, and these two. So we have three members left now. We have CE, CB, and EB left. So we go move on to the joint B, which was that support one. It has a support reaction of 244.45, and it has two members, BC and BE. And with sigma del Fy equal to 0, we get PBE sine theta, whose component is directed in the upward direction, plus 244.45 is 0. So PBE is minus 305.56, that is, it is an under compression. And we have this force left to find out. So PBC plus, because PBC is oriented around the x-axis only, and PBE has a cos theta component along this direction. So PBC plus PBE cos theta is 0. So we can find out the PBC as this in tension, and we have only one member left now, EC. This is the member we haven't solved it, and this is a joint we haven't used yet. We also haven't used C, but we didn't need to use joint C. So we move to joint E, and here we have EC, and these are two forces. Again, look why we have taken in like this, because this 305.56, this BE was under compression, right? So we will take towards the joint because it was under compression. And this member as well, this EF member, uh, we find out PEF as minus 183.33. So you will take this towards the joint. So we have one unknown, and we can use either equation, fx equal to 0, because okay, this is the, I guess this will be Pfy equal to 0, sigma Fy, because this is oriented on the y axis. So PEC equal to this force, its sine component will be along the y-axis. So PEC, its sine component will be pointing upwards, and PEC by default we have taken away from the joint, so it is pointing downwards. So PEC, we end up with a tensile force, 244.45 kilonewton. So we had, how many members do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 members. So we have 9 member forces, P1, P2, P3 to P9. We have found out all of them. Now we want to find out the horizontal displacement of the roller support of this truss. So what will we do? We will forget this 100 kilonewton. We will forget this 300 kilonewton. We'll remove those. We have to then note that you also have to change the support reactions. Obviously the support reactions were due to this loading pattern. These loads we remove, and we put a unit load at the roller. At this node A, we have to put a unit load in the horizontal direction, in pointing left or right, that's up to you. And you have to solve the reaction forces and the member forces again. So K system of forces, we will remove all external loading and apply unit load at roller support. Since you apply this here, you will see that now you will see that there are lot more zero force members. Like this was a zero force member, and if you look at this support, see, we have applied, okay, sorry, the roller is this, right? The roller is B, so we apply unit load at the point B, at the node B. We put a 1 kilonewton at B, so automatically the horizontal reaction at this has to be 1 kilonewton, and there will be no horizontal reactions. There will be no horizontal reactions here, because otherwise there will be an unbalanced moment. Like, you can solve it. I mean, you can solve it using the existing equilibrium equations, like sigma Fy equal to 0 and delta sigma moment equal to 0. You will find that there are no horizontal reactions no vertical reactions at this point, only a horizontal reaction of 1 kilonewton at this point. So if you solve this truss, you will see that this was a zero force member. Now if you look at this joint, in this joint what's happening, there is a member along the x-axis, and this member has, if this member had a non-zero force, it will have a component along the y-axis too also, but in the y direction there is no force, so this will also be a zero force member. Similarly, for this member, if it had a non-zero force KBE, then there will be no one to balance it, because at this joint B you only have an applied force of 1 kilonewton and a force PBC, but there is no vertical force, so this will also be a zero force member. Then you move on to this joint. See, basically, you are, if you can also, this that they have marked as zero force numbers, you can also solve it properly the way we solve using the method of joints. But these are shortcuts that will be really useful for, especially for competitive exams. So you can use logic and find out that these two are zero force members. Then you move on to this joint E. In E, what do you see? There is one member oriented in x direction, one member oriented in y direction. So obviously both of them have to be zero force members, because if this carries a non-zero force, who will balance it? There is no one to balance it, because the only other member is in its perpendicular direction, and you know that a force has no component in the plane perpendicular to it. So if at a node you encounter two members meeting at 90 degree, both have to be zero force members. They cannot contain any force. So if this does not contain any force, then you look at this member. At this joint there are two collinear members and one non-collinear member, this CF, so that will also carry no force. And since AF and FC both don't carry forces, at joint F again the same thing as with E happens. There are two forces, there are two members. This one actually, since EF also we know is a zero force member, FD also will be, because there is only one non-zero member force as far as we have gone so far. So this is a zero force member, so you can solve it and find that all of these carry zero forces, and only this AD, DC and CB are all under 1 kilonewton tension. That, of course, you can't just see and say it at this stage. So you will solve at each joint. Like at joint A, you will solve, you will find that KAD is 1, because conserving forces in the horizontal direction. Then at this point, joint D, you will have two forces, KDA and KDC. Since KDA is 1 kilonewton, KDC will also be 1 kilonewton, and similarly KCB will also be 1 kilonewton, all will tension. So we have 9 members, and if for the K system of forces, when there is only one unit load applied at the roller point, seven of them are under zero, six of them are under zero loading, and three have some component. So we draw this table of each member. See, there are 9 members. You will note down all the members. Then you will note down the P forces with the signs, which we have done. And there are only three. This makes your job easier, because there are so many zero force members in the K system that all of these terms in this product will become zero. So we identified the members that were not non-zero: AD, DC, and CB. So AD is one, DC is one, and CB is one. And the lengths, again, you have to calculate from geometry. They won't all be given, okay? Because in civil engineering questions, generally redundant information are not given. Like if one side of a right angle triangle is given to be 3 and the other is 4, they won't write the other is 5. So the hypotenuse, you have to find that out. So the angle also won't be given. They will give you the just the amount of information with using which you can find out all the other information. So the lengths here, where this was given to be 3 and this was given to be 4, so you know that this is also 4, these are 3, and all these hypotenuses are 5. So accordingly, you will take each member and note down the lengths, and the PKL product, this into this into this, is non-zero for these three members. You will add them, and you will divide by AE, that was constant for all. So you will this sum you will divide by AE, and you will get you are getting 2.33 millimeters positive. So what does this imply again? Since we apply the unit load along the pointing towards right, the displacement that we find out is positive. That means that this roller is getting displaced in the right direction. So this is the nodal reaction. So again, in this question, they could have given you to find out the vertical displacement at this joint. Then what would you have done? The P force, system force, will be same irrespective of wherever they ask for the displacement, but the K system of forces will vary. Then you will just forget about the external forces, and you would have applied a unit load at joint D in the downward or the upward direction, and then you would solve the forces in all 9 members. Maybe all of them would not have come zero like this, because that depends on the question. In here, it was really lucky that so many came out to be zero, but it may not be. So if there was a unit load here instead of here, then this won't be a zero force member, and from that you will find out the 9 forces again, the same way as you did for the P system of forces, and you will just find out the products, add them, divide by AE, and you will get the displacement of that node in the direction you have applied the force at. And the moment also similarly, like for example, you know that at a hinge or at a roller, there can be a slope. Like for a beam, in a beam, if there is a roller support, there will be some non-zero slope. But in trusses, we don't consider that. In trusses, we don't consider the slopes, we only consider the displacement. So far, in for the principle of virtual work in the unit load method, we have only considered this part. We have only considered that virtual unit force is applied at the node where we want to calculate displacement. This we have not tried yet. A virtual unit moment can be applied to a node if you want to calculate the slope. But for trusses, this is not relevant. We will encounter this later on when we resume beams, like especially indeterminate beams. So that part will be studied then. But so far, no, we have only we have only considered the translational part of it. So to find out the displacement in the x direction, we apply a unit load in the x direction, and to find out the displacement in the y direction, we apply unit load in the y direction at whichever node it is asked. Generally, of course, they won't ask in too many nodes, because you can see the process is lengthy. You have to solve the truss twice. Solving a truss for all its members even once is lengthy. You have to solve it twice, and it is a lengthy process. So that's why this table, you should memorize the columns of this table and just proceed in a systematic manner. Consider each member individually, and the lengths also put them down carefully. And as I said, the cross sectional area, just to give something different, they may say that the cross sectional area A in this term are different for different members. In that case, we have to add an extra column here for A, and find out the pkl by A for each and then add them. Okay, so are there any questions?
Ma'am,
Yes.
if we want to calculate the, in any case, we have to apply the horizontal
No, you
force
don't have.
at,
Repeat your question, please. In any case, do we have to calculate the horizontal load? What
in
did you say?
any, we have to apply the horizontal force at support, whether
No,
we,
no. You don't have to apply the horizontal force as the support. You have to apply the force in whichever whichever node you will be given. You will be asked to find out the horizontal or the vertical displacement at a particular node. अगर तुम्हें बोलता कि नोड ई में फाइंड आउट द हॉरिजॉन्टल डिस्प्लेसमेंट एट नोड ई, देन द यूनिट लोड यू विल अप्लाई विल बी एट ई in the horizontal direction. Okay, but
uh,
here the question was that find out the horizontal displacement of the roller support. So the roller support is at B, so we applied a horizontal load at this point B. Understood?
okay, understand. Thank you.
Any other questions?
Uh, uh, how can we
How can we what?
external virtual work and internal work? How can we equate internal virtual work and external virtual work, ma'am?
See, that is the condition in equilibrium. External virtual work and internal virtual work has to be equal. If they are not equal, then the structure is not under equilibrium. That is the what the principal virtual work says basically. And in the unit load method, the external work is that, since why are we applying unit displacement, unit force, so that the unit force is has magnitude 1, and that you are multiplying with the displacement at that point that you are finding out, so that you have to equate with the internal virtual work. That is what we are basically calculating here. This the formula that we are using, no, this
Yes, ma'am.
this formula sigma pkl by ae, this is the internal virtual work of the members. So that is what we are
Okay.
equating and directly finding out the displacement.
And ma'am, what do I, one more, that is Canny's method, ma'am. Canny's method is also similar to this, no, ma'am.
What is the spelling?
Canny's method, ma'am. K-A-N-I, Canny's,
K A.
apostrophe S.
I have not heard of the. Wait, I'll see what it actually is. Okay, it's some. I think it's a moment rotation method. No, this is not the same method, but yes, the moment rotation method is also used to find out the rotations and I mean the displacement and rotations at the different nodes. So that is a different method. That is a more general method that can be easily applied to indeterminate structures as well. But you'll learn it later. I think it is somewhere around week 10 or 11.
Okay, okay, okay. Thank you so much.
Okay. Okay. Thank you. Anything more? Okay, then I'll end the meeting.
Thank you so much, ma'am.
Okay. Thank you.